Okay. We are going to discuss today about graphs. So we have seen graphs before. How? In trees, right? These are also graphs, but they have a special property that there is something called the root node, the root, and then there are children. So there is a an additional structure on top of graph. Means you impose another structural constraint on graph, and that is what is the tree. But in more general, a graph can be defined as a graph basically has vertices and edges. Now, what is this V? These are the vertices or nodes. You know the concept of node, right? Vertices or nodes. And what is this E? These are called edges, or they're all also called links. Right? So if you want me to give you an example could be, let's say, you have now here, okay. Is this a graph? Is this a graph?
Yes, sir.
Yes, sir.
Yes, sir.
Is this a tree?
Yes, sir.
Yes, sir.
This is the root node. These are the children. But now, what about this? Is this a graph?
Yes.
Yes, sir.
It's a tree?
No.
No, sir.
It's not a tree because this has two parents. This is not possible. And similarly, what about this?
Sir, but until we show some direction, that
Yeah,
that
you're
means
right.
child as well.
Okay, yeah, you're right. Let's say this. You're right. So the tree is a directed graph because parent and children, they have some difference. Like parent to child versus child to parent, that is not a same thing, right? It's a different thing. There is a distinction in parent and child. Therefore, a tree is a directed graph. And in general, a graph could be directed or undirected. I'll discuss the kinds of graphs, but this is roughly, let's say you have some nodes and sorry, and there could be connections in between. Right? Any possible connections could be there, let's say. So this is a graph. So graph is a very general concept. So it has vertices, which are the nodes. Let's say this is V1. Let me, if I want to give some name, I can call it as just abstract name V1, V2, V3, V4, V5, right? So my V is essentially then, okay, let me write here. V is the set V1, V2, V3, V4, V5. I'm starting the numbering from 1. You can start from 0 also, no problem. So basically you have some class called a vertex, and it can have some data or some variables. I'm writing in short, but just understand what is the thing. Self dot value. It can have some value on top of it, some value in it, right? And that's it. this is how you can define a vertex. Every vertex can have some data. Then similarly, edges, you can name them as, let's say this is, okay, we can call it as this. Rather than calling it as E1, E2, I can call it as E connecting 1, 2. Or I'm not writing comma, just this does not mean E12, it means E1 and 2. Okay. Anyways, we don't have any 2-digit vertices, so this should be sufficient. And this is edge V, this is E1, right? This edge. Similarly, there is E1, 3, and so on and so forth. You can define a class. Who stops you from defining a class called edge? Here, it can have some weights. It can have some weight or it may not have some weights, right? Optional, it's also optional. So here value is optional, here weights are optional. For example, I can say, now give some examples. Can you give some examples of what kind of information can be represented with a graph?
Sir, it can represent a communication network.
Yes, very good. So let me write some examples here. In a communication network, a communication network, the nodes are what? They are the?
Sir, they are maybe computer or internet user, or it may be a core network, communication
Basic
network,
also.
servers.
Yeah. Let's say there are some data transmitting devices, right? Or data receiving devices, like transmitters and receivers.
Yes.
Transmitter or receiver. And this will be what kind of graph? It will be a directed graph, right? These are the receivers, receiver 1, receiver 2. This is an antenna, this is your mobile phones, something, right? And then there could be another transmitter. Now here, this could transmit to this, and this can also transmit to this, right? This is transmitter 2. And then it will have its own receivers, maybe. This is receiver 3, something like that. So this is a graph, right? It's a directed graph. If you allow the receiver also, like the mobile phone also can send data to the transmitter, then you can make it an undirected graph like this. Right? Because it allows two-way communication, means both the things are same. So this communication network could be represented. Similarly, what other examples? Yes.
Sir, transport network.
Yes, transport network. Let's say you have buses which are, this is Kanpur, this is Lucknow, this is somewhere now in between. Then, oh, but you cannot go to from Kanpur to Lucknow directly without passing through Unnao, right? So let's say there is no such path possible. Let's say somewhere Delhi, and you have separate paths connecting Lucknow and Kanpur to Delhi. Somewhere maybe, what else is there? Kolkata somewhere. And you have separate paths. Okay, Kanpur to Kolkata, separate path is there. Now, you may want to go from Kolkata to Delhi. There are two paths possible, right? Either the path Kolkata, Kanpur, Delhi, or the path Kolkata, Lucknow, Delhi. And which path you will take?
A minimum distance one.
Yeah, where is the notion of distance here? So you need to add some notion of distance to this ADT or data structure, ADT. So that is, so you will add some weight on the edge. This is an edge. Maybe the train takes 6 hours or maybe 10 hours from Kolkata to Lucknow, whereas a train takes 9 hours from Kolkata to Kanpur. Kanpur to Delhi takes 6 hours and Lucknow to Delhi takes maybe 7 hours. Kanpur to now takes, let's say, half an hour, and now to Lucknow takes, let's say, 40 minutes. So 0.4, no, not 0.4, it will be. Let's use the other notation. This is half an hour. This is, let's say, 3/4 of an hour. So that units are same everywhere. Okay, so this is my graph. Now you tell me if you want to go from Kolkata to Delhi, which path you will take.
Sir, via Kanpur.
Kanpur.
Via Kanpur will take 15 hours. This will take 17 hours. So definitely. So for such problems, you also need to have this weights on your edges, right? Okay, I think these are good examples. Let's move on. Now I will define some terms which I vaguely used here. What are the paths? Paths basically means it has a definition. It's an ordered sequence, right? It's a sequence of nodes, right? Which you will be following from Kolkata to Kanpur to Delhi. This is you cannot say Kanpur, Kolkata, Delhi. There is an order, Kolkata, Kanpur, Delhi, like ordered sequence of nodes. I'm using nodes and vertices as synonyms, so don't get confused. They are used as synonyms actually. Ordered sequence of nodes that are followed to reach from some initial node, let's call it as U, to some final node, let's call it as V. Node U to node V. So here, this was U, this was V, right? And since this is an undirected graph, so U to V or V to U does not matter. But if it were a directed graph, then U to V will be different from V to U, means because it's undirected. It's directed. Okay, I will discuss what is directed graph in a while. Now, this is the definition of a path. Like the ordered sequence of nodes followed to reach from node U to node V, including U and V. So here the path will be Kolkata, Kanpur, Delhi. Now, another term is closed path. So what is a closed path? Closed path is basically from this node, you travel everywhere and come back to the same node. You start from here. So basically here, this is a path with U equal to V, right? The closed path. Okay. Now another term is a cycle. What is a cycle? A cycle is a closed path. So here also U is equal to V, but there are no repeated edges. Here there could be repeated edges also. For example, you can say this path. Basically, from here you went here. From here you went here, then here, then here, then you went here, then you went here, then you came here, and came here, then again went there, and came back to this one. This is your U, this is your V. But you took a kind of eight circle path. And this is also a closed path because it reaches back here, but this is not a cycle. Cycle cannot have, so here this edge is repeated, right? This is a repeated edge. But a cycle cannot have repeated edges. Then let's take an example of connected graph, another definition, connected graph. So what is a connected graph? Let's consider this graph. This is unconnected, right? So because from here you cannot reach there. So connected graph is a graph with at least one path between every two nodes. There should be at least one path between every two nodes. So for example, here, if I pick up this node as my U and this node as my V, there is no path possible from U to V. So this is not a connected graph, right? Because connected graph should have at least one path between every two nodes. Okay. Now let's see another term called what is a directed graph. A directed graph is a graph where an edge can be traversed in only one direction. For example, if I have a graph like this, then this can go from then let's say U. So U to V is possible, but coming from V to U is not possible. This is a directed graph. For example, time always moves in one direction. So you cannot come back in time. So it's a kind of directed thing. So if you want to represent time on a graph, like different nodes are representing different events in time, then it will be a directed graph if you cannot go back. Then let's take another example. What is a complete graph? A complete graph, in a complete graph, every node is connected with all other nodes. Let's say, I think I drawn earlier also. This node is connected to every other node. This node is connected with every other node. This node is connected with every other node. And this node is connected. All the nodes are connected with every other node. This is a complete graph. Now tell me how many edges will be there in a complete graph if there are V vertices. So let's say there are. So V was a set. V is a set of vertices. When I put two lines on across it, it means the cardinality or the number of elements in this set. So which means the number of vertices in this graph. So let's say this is given to you. Tell me how many edges are there, number of edges.
EC2.
B, C, right? This is for an undirected graph, right? For an undirected graph, this is VC2. Now let's take an example of a directed graph. I'll draw just three nodes. Here, there could be a path here, a path here, a path here, a path here, be a path here. So here for V, what is the maximum number of edges?
Twice of that.
Twice of, which is basically VP2. So this is, if I write it, V times P minus 1 divided by 2. This is V into V minus 1. Okay. Yeah. Good. Now this is a complete graph. Then weighted graph, you already have seen what is a weighted graph. A weighted graph is basically you have weights on every edge, right? Like the Kanpur, Lucknow example. This is Kanpur, Lucknow, Kolkata, Delhi. Then you had some numbers on top of it. What were they? I think 9, 10, 7, 6. This is a weighted graph. Every edge has a positive weight. Okay, this is a weighted graph. Okay, let's now discuss about edges. This is just some terminology which will help you to understand the concept better. Let's say you can have an edge. Let's say this is a vertex. You can have an edge like this. Self-transition kind of thing, right? Let's say you are going. Right, this is also a graph, but the edges, this particular edge is called a loop. So what is a loop? It's basically an edge with same ends. It's an edge with same endpoints. Now, let's say, what is the concept of neighbors? Neighboring nodes. You have Kolkata, Kanpur, Delhi, and Lucknow. Tell me, so any two nodes which are connected by an edge, by a single edge, they are called neighbors. So neighboring nodes are the nodes connected by an edge. So tell me, are Kolkata, Kanpur neighbors?
Yes, sir.
Yes.
Yes, sir.
What about Kolkata, Delhi?
No, sir.
No,
No,
they are
sir.
not. They are not neighbors. Good.
Sir, if trees are graphs, then how are we defining neighbor for trees? Like the children and parent are neighbors also?
Yeah, you can call it like that.
Okay.
Because a tree is a directed graph, right? So they are neighbors. Now,
Sir, in trees, like parent and child are the neighbors, a parent and its child.
yeah, because they are connected by an edge.
Okay, but for the if we ask for a child, like its neighboring nodes, then only its child or its parent will also be its neighbor.
Yeah, good question. So if this was an undirected graph, in the directed graph, I have seen this concept of neighbors in the case of directed graphs or undirected graphs. I'm not sure in the case of directed graphs. I will let you know. Okay,
Okay, sir.
I will let you know this point. Okay, now let's talk about another concept called degree of a node. What is a degree of a node? Degree of a node is basically number of edges that are connected with that node. right? Degree of number of edges that are connected with that node. So for example, here, what is the degree of the node Kolkata?
Sir, 2.
It's 2. Yeah. And then a related concept is an isolated node. An isolated node is where degree of that node or that is equal to 0. The degree of that node is 0 for an isolated node. Right? So for example, here we may have let's say these are air paths. Then Kanpur has no airport. It is not connected with any of these. So it is an isolated node, right? Kolkata, Lucknow, Delhi are connected.
So an isolated node is an unconnected graph. You can say that.
Yeah, yes, there are no edges connected with that node. All right. Okay. Now I will discuss one concept called what is the density of a graph. The density of a graph is a concept. So there is a difference between this graph right? And this graph. Right? And this graph. Right? What is the difference between these three graphs?
So number of nodes are same, but edges are different.
Yeah. Yes. This is G1, G2, and G3. Now, number of nodes are same, but the number of edges are different. So they have got different densities. The density of this, let me call it as D. The density of this is 1. The density of this is 0. And this density is somewhere in between. So how is density defined? Density is related to the number of edges upon maximum number of edges possible, right? So in an undirected graph, the density for a graph G, which is basically vertices and edges, is defined as an undirected graph like this. It is number of edges in that graph divided by the maximum number of edges possible, maximum number of edges possible. Maximum number of edges possible for that V, which is basically equal to, you had just defined it, right?
VC2. Yes, sir.
VC2, right? V. And but if the same thing comes to an undirected graph, to a directed graph, then the definition remains same. This part remains same. Maximum number. This is for the undirected graph. This is for directed graph. Right. So this becomes number of edges upon twice of VC2. Right. So this is the definition of a density. Definition of density. Now the density for this graph is 1. Density for this graph is 0. What is the density of this graph? Quickly. D equal to what?
Point 0.5.
0.5.
0.5. Okay, let me see. 1, 2, 3, 4, 5. 5 upon 5C2. It is 5 into 4 upon 2, right? This is equal to 1 upon 2. Density is half. Okay, now that's it. I think these were the major concepts. Now let's come to some data structures. How do you represent a graph? How do you represent a graph? The data structure.
Sir, we can use a matrix or a two-dimensional array.
Okay. Then
Sir, a node can consist of a value and a list of edges.
the node can consist of value and,
A list of edges.
oh, you're saying that you will be defining a node data structure.
Yes, sir.
So where you will have something, let's say a class node, which will have, if I say define init, etc. Here inside this, you will have
A value,
some value and
list of edges.
This is an undirected graph, right? An undirected, or yeah, this is an undirected graph.
Yes, sir.
Yeah, correct. And then this will be a list of edges. So let's say, but then this edges also, you have to say, a little difficult. Now, what will be the edges then? What will be edges? This will be another class, right?
Yes, sir. Which will contain its source and destination nodes and the weight.
This will become very complicated, no? Here,
Yes, sir. Yes.
self dot, let's say, source and destination, and then the weight. Yeah, this is correct. So basically, the instances of these edges will be here. Yeah, this is a valid way. Yeah, valid way to do it. It can be a little complicated, but yeah, it's a valid way. Yeah. So in this way, you can define whatever you want as nodes. And in case, another way is instead of defining edges, you can just say self.neighbors. If your edges are not weighted, right? You can just define your neighbors. And if they are weighted, you can also add self.weights. Which will be again a list. This is a list of other nodes. These are just numbers, and corresponding to these nodes, they are basically, there is a one-to-one correspondence between neighbors and weights. Yeah, this is another way. Yeah, it's the same thing. Okay. Yeah, so in this way, you can represent your graph. Any other way to represent a graph?
Sir, can we represent the neighbor and weights together like in a dictionary?
In a?
Like a dictionary.
Yes. Yes, you can do that. Yes. You can combine these two to form a dictionary also. No problem. Okay. So another way to represent a graph is list of edges. Just a list. You can say E is just a list. let's say here, V1 comma V2 comma, let me write a graph first. Simple graph. Let me write. That's it. So this one will be V1 comma V2, V1 comma V3, and V2 comma V4. That's it. This is the graph. And of course, your V's are V1, V2, and V3, and V4. This is not required because you can just read these from here, but just in case I'm writing. Yeah, but this is sufficient, right? Because from these entries, you can get the value, the V1, V2, V3, the unique values. This is sufficient to say this is my graph. Right? This is a valid way to represent a graph in data structure. Another way, which is maybe a little different, it's called an adjacency matrix. So what is an adjacency matrix? It's a matrix. Let's say this is 4. So this will have 4 rows and 4 columns. V1, V2, V3. Now, wherever there is an edge, you add a 1 there. Between V2 and V1, there is an edge. V2 and V1, you add 1. Since this is an undirected graph, it will be transpose, means let's say if I call it as A, then A transpose is equal to A. In case of an undirected graph. For a directed graph, this won't be true, right? So V1, let's say this is my source, this is my destination. Then V1 to V2, there is a path. V2 to V1 also, there is a path. Now, V1 and V3. So V1 to V3, there is a path. And V3 to V1, there is a path. Then V2 to V4. V2 to V4, there is a path. V4 to V2 also, there is a path. And V1 to V1, you can keep it as 1. So all diagonal entries could be 1. Or you can call it as 0, keep it as 0 also. That doesn't matter because we are not considering loops here. If there are some loops, you can put the values of loops. And and other things can be 0 actually. And in case you have weighted, this was an unweighted graph. If you had weighted graph, you could have put weights also here. Right? So if it were a weighted graph, you could have put the weights here. Okay. This is an adjacency matrix. This is another representation for graph.
Sir,
Yes.
so then instead of 0, shouldn't we write infinity because the unconnected nodes will have infinite weight. If there
Okay.
is
Okay. Yeah. That depends on your convention. That's your convention. If you call it as let's say the connection strength, right? If A is your connection strength, then you will say it as 0 strength, means there is no connection. If you call it as distance, then you may call it as infinity. Means, see, you are defining things, so this is in your control, how you want to control. Let's say each entry represents connection strength. Or you can define it in such a way that Each entry represents distance or connection or closeness. How close they are means how similarities. You can say similarity, right? Or similarity. Means you can, in different contexts, you can define it in different ways.
Okay, sir.
So there are, yeah. So here, if you want to do, if you want to go from path from let's say V2 to V3, you will maximize your path, right? You will maximize the sum of weights along your path, right? And you will maximize the sum of weights along the path, right? Whereas here, in case of distance, you want to minimize your sum of weights, right? Right. So let's say this is 2. This is for 1. All right. Okay. So this is the thing. Now, these are 3 representations for a graph. And depending, okay, now let's see, when would you prefer one representation over the another? When would you like to use adjacency matrix?
When the number of nodes are very high.
When the number of nodes is very large, so your size of your adjacency matrix is basically B cross B, right? If your number of nodes is very high, then this size will be also very large.
Sir, for complete graph, we should prefer this matrix.
Yes, yes. For complete graph, or when D is high, when density is high. Good for high density graphs, you can say. High density graphs means most of the nodes are present and the very less nodes are 0, or very less nodes are absent. Sorry, very less edges are absent. Sorry. Whereas, so this is the thing. And when do you prefer the other? When do you prefer the other representations? List of edges or a node data structure? This is
When
preferred
density is
for,
less.
for sparse graphs, which means my density is very, very small. Right?
Yes, sir.
And this will also be useful for sparse graphs. But now see, yeah, both are valid representations. The advantage of this is that if you know the node, you immediately know your neighbors. But here, if I tell you the node E1, V1, what are the neighbors you have to search? The complexity for that will be of the order of number of edges, right? But whereas here, the complexity will be of the order of what? It's O1, right? So let's say there's an operation called find neighbors. Let's write some functions which are possible in this ADT called graph. So there is a function called get neighbors. Given a graph, and it could be self also, comma, I give you one vertex V. Now get neighbors. So you can define this, right? It just returns a list of neighbors. Okay. So tell me, what is the complexity in the above three representations? In the first representation, what is the complexity? O?
Sir, 1.
O1. Yes. In the second representation, what is the complexity? O?
So number of vertices. Over
Number of vertices or?
Edges, sir.
edges.
Number of
Sorry,
edges.
edges.
Yeah, no problem. In the third representation, adjacency matrix.
Number of edges, sir.
This is 1, this is 2. Yeah, again here, this is number of. Right. But other things are different. Let's say I want to compute the density of a graph. Means this is not a very standard function, but
Sir, in adjacency matrix representation, we have to search the whole matrix and see which elements are 1 to find its neighbors, right?
in the adjacency matrix representation, you have to search the entire row.
Oh yeah, entire row. So it should be number of nodes, not edges, right?
Ah, yes, you're right. You're right. Thank you. Thanks for pointing this mistake. This number of nodes. Yeah, thank you. Now compute the density of a graph. So in the first case, what is the complexity?
Number of nodes. Like for each node, we can get the length of edges list, and then we can calculate the density.
For each node, you can get the,
Length of this list, self dot edges,
yeah,
and that's
yeah. You have to go to each node. Yes, so it's number of nodes. You will be doing a graft reversal here, right?
yes.
Like it could be a, we will discuss some graft reversals, graft reversals. Okay. For the second representation, where you have list of edges,
Yeah, it's a big of 1 because we can directly get it, length of
yeah,
it.
yeah, you just find the length of E and that's it. You just have to find length of E upon some number, which is V times 1, V minus 1 upon 2. This is, if your length is readily available as in an array, then it's just O1. For the adjacency matrix,
Big of 1.
O1, because just sum up all the entries. That's it. Right?
Sir, if the edges carry some weight,
Yeah,
okay, we can consider all the edges 1 weighted. Yeah, fine, sir.
yeah. Okay, now let's go to graft reversal. How do you traverse a graph? How do you traverse a graph? I give you a complicated graph of cities in India. How will you traverse this graph? Okay. There are two ways. You have already read these ways in the trees. One is called depth first search. What are the depth first search methods did you study in the trees, in the binary tree, or in the tree in general? You studied pre-order, in-order, post-order, right? Both these methods, all three of these methods, they do depth first search. They will go all the way down to the root, come back, again go to the next root. No, not root, but the leaves. Starting from the root, they will go all the way to one leaf. Then they will go all the way down to another leaf, all the way down to another leaf. So this was called depth first search, right? But another way is breadth first search or level order search. Where you basically do a traversal where you take this level, then this level, then the next level, then the next level. That is called breadth first search. These are two methods for graph traversal, right?
Sir, how can we define labels in a graph?
Yeah, basically neighbors, right? You will go to one level of neighbors, means starting from this node, let us say, you can start your traversal from any node, right? There is no root here. But let's say you start from this one. Then you will go to first neighbors, this one and this one. Then the next level of neighbors, this one, this one, this one. The next level of neighbors. The method is same. You apply a queue here. This uses a queue. And this will use a stack or recursion. Basically, recursion also is a stack only. Stack or recursion, right? Let's say if you are given a node, example. Let's say I define your node in this way. It has got the value. Let's ignore the value. There is some value, but let's consider that it has the neighbors. It's a list of other nodes, which are its neighbors. Then how will you do depth first search? Define starting from a vertex B. Let's call it as a different class graph. Let's say I will define it like this. Something. And then you initialize it in some way. It means I'm not going into details, and there is a function called depth first search. Starting from a node, how will you do it? Let's say I want to just print the values. Let's say every node has got some value also. Okay. Otherwise, how will I? Some value, some integer is there. Let us say. How will you do the depth first search? You can do it in a pre-order fashion where you will say, okay, first print u dot value, right? And then you apply a recursion where you will say for v in u dot neighbors, right? You apply a depth first search on each v. That's it, then return. Right? Does that make sense?
Sir, shouldn't we keep track of all the nodes we have traversed so far?
Very good. Very good point. So this is not a tree. In a tree, there are no cycles. But here in graphs, there could be cycles. And let's say, when you say this is a neighbor of this, then this is also a neighbor of that. So if you run this algorithm, it will come back to itself. Basically, you start from U, go to V, and in the neighbor list of V, U is also there. So you come back to U. So you are caught in a loop or in a cycle, and you are caught in many cycles, and they'll be infinite. This algorithm will not terminate. So what you have to do is you have to maintain a list of all the nodes that you have traversed. Okay. So let's say we maintain a list. I can pass that list along with this, or else I can keep it as a global variable. Both the methods are all right. Let's pass it along. This is called traversed nodes. I will just call it as TN in short. TN are the traversed TNs, traversed nodes, all right? So now what I will do is, I have got a U, I've got the list of traversed nodes. I can either do a check here or I can do a check later. Let me do it here itself. If U in traverse nodes, then return, right? If U is in traverse nodes, then return. Otherwise, the method will continue. So you will print the value of U, right? And then you will do this. But you have to again here add your U into the traverse nodes. So you will say traverse nodes is it's a, let's say, a list. So you will say TNS dot append U. So you will add your U in the traverse nodes. Then here you will apply comma the updated TNS, right? Does it make sense?
Yes, sir.
Yes,
Will this algorithm work now?
yes, sir.
Yeah. So this is how you will be. This is how the you can do depth first search. And similarly, this is and similarly you can do breadth first search. Let's say I define something called BF. I want to start from a node U. So what will I do here? In breadth first search, what will I do? I have to define a queue, right? I can define a queue, and so my algorithm will be like this. So you do the print, the U dot value, and then you have to add all the children in the queue. I will say for children in, sorry, not children, but the neighbors. In u dot neighbors, then you will add, you can define that q as a global variable also, right? Here. Okay, I'm just defining it here, but it could be either in the init function or somewhere. It means, okay, let's see. So here you will say q dot, q has a function, q has nq, dq, all those data structures. All the nq, dq, etc. are available. So I will say my q dot so q dot nq. I will nq all the neighbors, and then I will pop the. Oh, I think this will become a little complicated. Means okay, we can complete the code. So basically, you will nq all the neighbors in the queue, and then you will be popping them out until you get until all the queue becomes empty, right? And then again here you have to maintain the TNS, the transversed node list. You can also define as a global variable. TNS is equal to an empty list in the beginning, and you have to check here if your U is not there in TNS, then only you do it. If it is already traversed, then you won't do it, right? Otherwise, you print it and then you do TNS dot append TNS dot. Right? And then you will be enqueuing all the children, and then you will be doing, you'll be calling this BFS over and over again. You will pop basically or dequeue an element from queue and then call it. Right?
Yes, sir.
After the end of this for loop, we should dequeue u, right, from the queue.
Yeah, you can do that. Do we do it like this? No, q dot dequeue. That's it. And then no, this is not how we do. Okay, but here if u is none, then you stop. You don't do it. If u is none, then you return, which the queue is empty. Otherwise, you do self dot BFS of u, and then again it will go into the BFS of u. Here, okay, we are adding nodes into our TNS set, even without checking. It's possible that here itself we can put a check if V is not in TNS. then only you enqueue it. Otherwise, don't enqueue it. And this way it is more convenient because you can directly, I mean, you need not save too many things in your queue. Okay, yeah. Okay, I have not run this algorithm. There might be some changes required here and there. So you can do it. Okay, so fine. This is how I can do traversal. Basically, two kinds of traversals are there: depth first search and breadth first search in a queue or in a graph. Okay, so any questions here? Any questions here?
Sir, if we have to find a path between two specific nodes, so there will be multiple paths. So
Yeah, you have to write the algorithm. You can write. You have to write an algorithm how to go from this node to that node in the shortest possible way.
okay, sir.
Shortest possible path. You can do either a depth first search or a breadth first search, right?
Okay, sir.
Because you don't know the path, no, means how there is no directionality here. So you have to either do a BFS or a DFS to find the other node. And as soon as you find it, you will just note down that path.
Okay, sir.
Right? So DFS or BFS will be required. Okay. With that, we can either stop here or we can take up a practice problem. Right?
Maybe in next class.
Okay. Okay. Yeah, I think. All right. Then I will just write the problem which you can practice on your own.
Okay, sir.
This is a simple problem of traversal, graph traversal. It's called copying a graph. I want to make another copy of that graph so that I can modify it. So I give you a graph and I give you a node, which is basically, I define this node in this way, as we have defined here. Did we define the node somewhere? Yeah, this is how we define the node. So I define this node. If I define my node in this way, then the task is, I give you a given graph. Basically, I give you a node which has got its neighbors and it's a connected graph, etc. Given a graph, basically, in the form of a node only. Create a copy of this graph. Okay, so basically, if I give you this graph, then you have to create a copy of this graph, which will be a separate, another graph, where let's say this is some V1, V2, V3, or let's say some data is present here. Some data is present here, some value is present here. Let's say this has Kanpur, Lucknow, Delhi. Then I want you to return the graph, Kanpur, Lucknow. Same graph you have to return, but just that here you have to make a separate copy so that if I modify this graph does not get changed, right? Copy, let's say G dash of G such that modifying G dash does not modify G. Right? I can simply say G dash is equal to G, right? But this won't make a proper copy. It's called a deep copy. Rather, it will just make another pointer to the same graph, right? So let's say this is my G, this is my G dash. But if I do it like this, it will simply create another pointer G dash to this graph. It won't create a new graph, but I wanted a new graph. So this is the problem. So what you have to do here is, starting from the node N, you have to do the graft reversal and then make this copy, right? This is when this kind of representation is used. But if you use some other representation, let's say the second representation where you have a list of edges, then it's very easy, right? Copying a list is very easy, or traversing a list is very easy. Or if I give you the adjacency matrix, then again, the copying the graph is very easy because you can simply copy the adjacency matrix. Okay. All right, so basically, this is the problem. You can spend time on it. This will help you to learn more about graphs and practice a bit. Okay, and your second assignment is already on, means you're already doing the second assignment.